The concept of waves have been understood and studied for thousands of years. Waves can be observed in various phenomena such as water waves, rock waves, and seismic waves in earthquakes. The ancient Greeks were among the first to study the behavior of waves, with philosophers like Pythagoras and Aristotle investigating the properties of sound in string and percussion instruments. However, very little was known about light. The idea of light as a wave was first proposed by English physicist Thomas Young in the early 19th century. In his famous double-slit experiment, Young showed that light waves undergo diffraction and interfere with each other just like waves in water, suggesting that light is a wave phenomenon. But this is baffling because light travels the vast space between the sun and the earth without any medium. That mystery was solved by James Maxwell. He formulated a set of equations that describe the behavior of electric and magnetic fields as they propagate through space and showed that these fields can be combined to form self-propagating waves. The electric and magnetic fields are perpendicular to each other and to the direction of propagation of the waves, as illustrated in this slide. Other than light, microwaves, X-ray, ultraviolet, infrared, and radio waves are also electromagnetic waves. Take a moment to study the chart. The important point is to get a sense of the order of magnitude of the wavelength of these waves. The human eye is only sensitive to a narrow range of wavelengths within the electromagnetic spectrum, known as the visible spectrum. The visible spectrum includes the color of the rainbow, which have wavelengths ranging from about 400 to 700 nanometers. These wavelengths are within the range that the human eye can perceive and are detected by specialized cells in the retina called cones. Can anyone tell me what is the outermost color of the rainbow? Electromagnetic waves carry energy in the form of oscillating electric and magnetic fields. The energy of electromagnetic waves is directly proportional to its frequency and is described by its photon energy, which is the energy carried by each individual photons that makes up the wave. What is the photon? Well, in short, it is not in your syllabus, and I leave that to the curious mind to find out on their own. The energy of an electromagnetic waves can be transferred to matter when the waves interacts with it. For example, when light waves is absorbed by a material, the energy of the waves is transferred to the electron in the material, which can result in the excitation of the electrons to higher energy levels. The energy of electromagnetic waves is also related to their wavelength. The shorter the wavelength of an electromagnetic wave, the higher its frequency and energy. This is why high-energy electromagnetic waves such as X-ray and gamma rays have short wavelengths and can be harmful to living tissues. The energy of electromagnetic waves plays a critical role in many fields, including communications, medicine, and astronomy. For example, in medicine, the energy of an electromagnetic waves is used in diagnostic imaging techniques such as X-ray and MRI, while in astronomy, the study of energy emitted by electromagnetic waves from distant stars and galaxies help us to understand the nature of the universe. That's all for this section on light as an EM wave. Check out the other videos.